Hello, everyone. We're going to get started here in just a few minutes. Let me just get some things set up. Okay. Looks like we're good. Okay. Just getting some things set up here. Thanks for being patient with me as we get going on this. Okay. My name is Beth. If you are here, please let me know in the comments. Say hello. I'd love to see who's here, get some engagement that way. That would be great. If you're new here, you know that would be great. I love to have new faces here. If you know me and you've been following me, let me know as well. If you're looking for ways to support me, I've got some things listed here for ways to support me. It does really help because I do private tutoring as my primary source of income, and YouTube I've been working on since around 2014 actually, and it's been it's been fun, but it is definitely a lot of to make all the videos and everything. So let me know if you're here. And we're going to get started on some pre-algebra and algebra 1 skills for today. I kind of mixed things up for today. The students that I've been working with recently in pre-algebra, I've been doing more with transformation. So I wanted to include that in my lesson for today. And then in algebra 1, we are going to be working on multiplying monomials and polynomials, and then also factoring. So that's what's coming up later on. I'm going to try to spend about 20 minutes on each subject. Okay, well, let's go ahead and get started. Again, all of my pages that I'm using for today's lesson, you can find at this website, Kuda Software. If you want to download, it's a free website. You can download these worksheets or print them out, and you can work along with me if you would like to. All right, so we're going to talk about translations on this first set for our transformations for today. We're going to work on translations and then also rotations next. So for translations, think slide. We're moving things up, down, left, right. Sometimes a translation can just be one movement, so one direction, like maybe up or just to the right. Sometimes it can be two, like up and to the right. So So we're going to cover both of those types today. So with translations, it's really pretty simple, especially when you have it graphed like this. The translation it's telling us to do is 1 unit left. So that means that this entire figure, this is what we call the pre-image. This entire pre-image is just going to get shifted over 1 unit to the left. So each of these vertices, I'm just going to rewrite over here 1 unit to the left. So now this new point, we're going to write as x prime. So this little mark here kind of looks like an apostrophe. That's what we call, we say prime when we are using that mark. And then for G, we're going to mark our new image point at G prime. So just 1 unit over to the left, 1 square over. For Q, we're going to move that over, Q prime. And then for U, we're going to move that over to the left, U prime. And so then we are going to connect. Actually, let me use a different color here so we can make sure you see this. We're going to connect all of those points with straight lines. Now, we did have a graph for this one, so it was pretty easy just to count 1 unit over. If we were given vertices, so let's say, for example, for G, so the original image G, the pre-image was at, looks like 1, 2, 3, 4, 4, 0. That was the coordinate for the original vertice at G. And so then G prime, what we can do, 1 unit left, the left is going to affect only the x portion of the coordinate. So that means whatever is in our x position there, we're going to subtract 1 since we're moving it to the left. And so 4 minus 1 would equal 3. And then the y doesn't change at all when we are just moving to the left. If they said up or down, that's what would affect the y portion of the coordinates. We'll go over that in problem 2 because in problem 2, we have 2 directions. Our translation for this triangle, TEI, is 1 unit right and 2 units down. So let's go ahead and just show that on the graph. Again, let me do like a different color here. I'll do green. So 1 unit right, 2 units down. So I'm going to start with vertex T, and I'm just going to count 1 unit right and then 2 down. So then that's where T, let me write it up above, T prime would be located. For E, 1 unit right, 2 units down. So that's E prime. And then for I, 1 unit right, 2 units down. So that's I prime. And we're going to connect all of those points. And then again, just to show you what this would look like algebraically or with the coordinates, you might see these directions as written as this. It will look like this with x, y, and an arrow. And then for the x, because we're moving 1 unit right, then that's going to be x plus 1 because we want whatever that x value is to shift over to the right 1 unit, so going higher, more. And then comma, and then y, 2 units down would be a minus 2. So this is how you would write the translation algebraically. And then for the actual coordinate, let's take a look at coordinate E. So the original, the pre-image, E is at -1, -1. And then if we were applying these rules, E prime would be x plus 1, so that's now 0. And then y minus 2, so that's now -3. So see, I've just added 1 to my x value, and I've subtracted 2 from my y value. And so that's how we wind up at 0, -3, which is where we wound up with our E prime. Okay, so that is how to actually do the translation. Now we're going to write a rule to describe each transformation. So these are going to be just translations, not any other kinds of transformations like rotations or reflections or anything like that. So again, since we have the graph, we're just going to count, and we don't even have to count all of the vertices. We just have to pick one because they're all going to have the same rule that's applied to them. So I'm just going to pick one. We can tell that the black quadrilateral here is the pre-image, the original, and the blue one is the new image because they have the little prime marks next to each of those vertice names right there. Okay, so it looks like for this one, for number 11, if we're looking at u and u prime, we're just going up 1, 2, 3, 4 units. So then we could write this as a translation, 4 units up. Or if we wanted to write it algebraically, we could write it as x, y with the arrow. And then for x, we didn't do any changes to x since we moved up. We didn't move left or right at all. So x is just going to stay x. But then for y, we're going to do y plus 4. So that's how you would write it algebraically. All right, let's take a look at problem 12. And so again, it looks like this quadrilateral, this black one, is the pre-image, and the blue one is the image. So that's the new one. So I'm just going to pick a point that would be easy to track. I'm going to go with D and D prime here. So let's see. We moved 1, 2, 3 units to the right. We're just going to write a plus 3 there. And then 1, 2, 3 units down. So I'm just going to write a minus 3 there. So our rule is a translation. 3 units right and 3 units down. It doesn't matter too much if you do the up and down first and then the right and left, but typically just because our x's go first and then our y's, like that's how we write our coordinate points. We write whatever the translation is for right or left first and then the up or down. So that's why I chose to write that one first. And then for algebraically, we're going to write x, y, and then our arrow. So then for the x, we added 3. And then for the y, we subtracted 3. So that's how we write it algebraically. Okay, so that's translations. Now we're going to take a look at rotations. I have a really cool way of remembering how to do rotations with the coordinate points. So I'm going to actually to write that over here on the side really quickly. I kind of go into this in more detail in one of my videos that I just recorded recently. I have all of those videos linked for you in the description below. So look for that video about transformations with rotations, and I go over this rule in more detail. So for counter, so sorry, trying to write and talk at the same time doesn't always work. So we've got 2 different types of rotations. We can either go counterclockwise, which is going around to the left, or we can go clockwise, which is going to the right, around and to the right. So let's start with counterclockwise. So our normal coordinate is an XY coordinate. What I'm going to show you is how to determine what those coordinates are when you are being asked to rotate counterclockwise or clockwise, and then a certain number of degrees. So if we're asked to rotate 90 degrees counterclockwise, what we're going to do is we're going to actually rotate our x and y's. So I'm going to take this y and rotate it around to the other side of the x. And whenever we move one of our numbers, we are going to change the sign. So now for a 90-degree rotation, our coordinates would look like this. We would have a negative y, x. So that means that whatever that coordinate is in that vertex, we will switch them. And whatever y was is now going to be the opposite sign. Okay, if we're asked to rotate counterclockwise 180 degrees, then we're going to go from here, and we are going to just, again, take this, whatever was in this one position and move it one more time, rotate it over to the left, and change the sign. So then again, this is going to be negative x, and then that negative y stays the same. It just gets shifted over to the right because the x pushed it out of the way. All right, and so then if we are asked to rotate another time, 270 degrees, then we're going to do the same motion again. And so now our new coordinate is going to be now positive y, x. So all of these that are listed here are all in relation to our original point. So this is something that you can just write out on the side of your paper, and then you can have that available for you as you're doing your different rotations. Clockwise is going to be the same thing, but we're just going in the opposite direction because we're going from the left to the right. So for a 90 degree, we're going to take the X and move it over. We're going to rotate it over to the right-hand side. So now our new point is going to be Y negative X. And then for a 180 degree rotation, we're going to make that Y over, move that Y over to the other side. Now we've got negative X, negative Y. And then for 270 degree, we're going to rotate it again and again change the sign. So now the negative Y is first, and then X goes back to being positive. So let's put that into practice. Hopefully that makes sense, but if it doesn't, hopefully once we put it into practice, it'll make sense. Another thing to note is that the 180 degree is the same for both clockwise and counterclockwise. So if it's asking you to rotate something 180 degrees, it doesn't matter if it says clockwise or counterclockwise, it's still going to be the same rotation. All right, let's take a look at this first problem. Here we go. We're being asked to rotate 180 degrees about the origin. So notice it didn't say clockwise or counterclockwise. And that's because, again, it's the same thing. So what I'm going to do is I'm going to list my points, Q, J, and H. Q is at 0, -1. J is at 1, 2, 3, 4, 5, -5, -3. And H is at -3, -5. All right, so now let's take a look at what's happening with our 180 degree rotation. The X and the Y stay in their same position, but the signs are going to change. So then that means that, let's see, I'll use purple, I guess. So for Q prime, for 0, there's no such thing as positive or negative 0. So 0 is just always going to stay 0. But then our -1 is going to change to a +1. So I'm going to go ahead and graph that at 0, +1. So that's where Q prime is going to live. For J prime, again, these don't switch. The signs switch. That's the only thing that changes about a 180 degree rotation. So for J prime, we've got 5 and then +3. So that's J prime up there. And then for H prime, again, we're just switching the signs. So now we've got 3, 5, 2, 3, 5. That's H prime. And then let's connect all of our points with a straight line. So we can see that this triangle has just rotated up to this first quadrant from the third quadrant. Okay, let's do another rotation. This one is 90 degrees counterclockwise about the origin. So we're going to be using this rule right here, -yx. So all that means is that we're going to be switching the x and the y in their coordinates. And then whatever was in the y position, we're switching that sign as well when we switch it to that x spot. So let's, again, first just list out our original coordinates, B, S, and L. So B is at 4, 5. S is at 2, 2. And L is at 5, 0. All right, and then let's use this rule to write out our new coordinates and graph them. So B prime, we're going to switch, and whatever was in this y position is going to switch signs to. So now we have a -5, +4. Notice that the 4 stays positive. It's just moving positions. And then let's go ahead and graph that. So -5, +4 would be right here, B prime. S prime. Well, since both of these numbers are the same, we're not gonna be able to see the switch too much, but this 2 does move to the x position, and we're gonna make it negative, and then this 2 switches to the y position, and it stays positive. So -2 and then +2, so that's going to be S prime. And then L prime, we're going to switch. Again, 0, there's no such thing as -0, so we're just gonna keep it as 0, and then the 5, so this basically just switches. So we've got 0 and then 5. So that is L prime. And then let's connect our points. so we can see how our triangle is rotated. So it is just rotated over to this second quadrant. All right, in these last two problems, before we get to our algebra work, we are going to write a rule to describe each transformation. So some people are able to do this pretty easily just visually. Knowing the quadrants are going to help a lot. But again, we can use, actually, let me grab my rules up here. We can use these same rules. The nice thing is with this, we don't have to do it for every single vertex. We can just do it with one. So what I'm going to do is I'm just going to look visually. It looks like this is my original. The black is the original and the blue is the new. And it looks like it's just rotated this way. So to me, this says 90 degrees clockwise. But let's confirm that with our vertices. So our original N vertex, we'll label N as 5, 4. Sorry, excuse me, negative 5, 4. And then our N prime, it looks like it is at 4, 5, positive 4, positive 5. So let's see what's happened here. It looks like our X and Y's have switched, so I know it's not a 180. And the original X was -5, but then when it moved over here, it got switched to a +5. So that tells me this rule right here. The X and Y are switched, and the X has changed sign from its original sign. So this is a 90-degree clockwise rotation. All right, let's look at number 12. So again, I'm just kind of looking visually to see when the images are diagonal to each other between the different quadrants, that signals to me 180 degrees. And 180, you can write clockwise or counterclockwise. They're both the same thing. When it's 180, we normally just say a 180-degree rotation. But let's go ahead and confirm that with one of the vertices. I'm going to go with T here. So T, original T is at -4, -3. And then T prime is at +4, +3. And that is consistent with our 180-degree rotation. The X and Y don't switch spots, they just switch signs. And these were both negative before, now they're both positive. So this is a 180-degree rotation. Okay, excellent. We are going to take a quick break. Let me put this up on the screen. We're going to take a quick break for just a minute. Let me check in with the chat and then we'll get into some algebra as well. Okay, let's go ahead and get into our algebra section. We're going to be talking about multiplying monomials and polynomials. This one I think is going to be a lot quicker. The transformations sometimes take a little bit longer with transforming all of those vertices and then graphing it and all of that. So let's talk about multiplying monomials and polynomials. So and again, these are from CUDA software, so you can download these pages and work along with me if you would like. So monomials meaning one, polynomials meaning many. So these are talking about the terms that we're multiplying. I've got a couple. I'm going to call this beginner, intermediate, and expert level. So I've kind of started off easy here, and we're going to work our way through to the more challenging problems. Whenever we have any, just like the distribution property that we learned about many years ago, um, whatever we have on the outside here is going to get distributed to each term inside of our set of parentheses. So let's start with this first multiplication. When we're multiplying terms that have variables in them, the rules can be a little bit tricky at first. So we're just going to go ahead and multiply the numbers first. 8 times 6 is 48. And then an x times x, we're just going to write as x squared, right? Because anything times itself, we can write with that 2 exponent. So we're just going to call that x squared. All right, and then we're going to distribute this 8x to the 6 as well. So you can multiply these. I know a lot of times students get tripped up on if they are like terms or not. Like terms and combining like terms is only applicable when you're adding and subtracting terms. When you're multiplying, you can multiply any type of term times another term. So we're just going to do the same thing. We're going to do 8 times 6. So that's a positive 48. So I'm just going to write plus 48. And then since there is no variable with this 6, then we just have that x there as well. Because remember that this 8x really means 8 times x, right? So we're just multiplying all of these numbers and variables together. And typically when we write numbers and variables that are multiplied, we don't put any symbols in there. We just kind of squish them together. All right, and then that's it. That's as far as we can go with this one. So that is multiplied and simplified. All right, let's go to problem 7. So we're going to do the same thing. The only thing that's different about this one is that we have 2 different variables, and that's okay. So the same process here. So 7x times 6x, we're going to multiply those numbers. So 7 times 6 is 42. And then x times x is x squared. So that's pretty similar to what we saw before. Now we're going to multiply 7x times 4y. So again, we're just going to multiply the numbers. 7 times 4 is 28, so it's a positive 28. And then x and y, they are 2 different variables, meaning that they are representing 2 different numbers. So we don't know what those numbers are, so we are just going to write x, y here behind the 28. So all this means is that 28 is being multiplied times x and by y. So all 3 of these things are being multiplied together. We just don't know what those x and y's are, so we can't really simplify it any more than that. All right, and then our last more challenging problem for this, we've got 2u on the outside here. Let's go ahead and multiply it times this first term. So again, we're just multiplying the numbers. 2 times 6 is 12. And then a single u times 2 u's that are being multiplied together would give us 3 u's being multiplied together, right? That part is sometimes challenging for students that I'm working with. So I'm going to write this out again. So 2u represents 2 times u times 6 times, and then this u squared is u times u. Okay, so now let's take a look at what we've got now that we've kind of have it expanded out there. The 2 times 6, again, with multiplication, you can multiply in any order that you want. So we're going to put the 2 things together that we can put together, which is the 2 and the 6. We know that that equals 12. And then we've got 1, 2, 3 u's that we're multiplying together. So that's where the exponent of 3 comes from. All right, let's continue. And we're going to multiply times this middle term. So again, 2 times 9, we're going to count this as a negative 9. So 2 times negative 9 is negative 18. So we're going to write minus 18. And then u times u is going to give us u squared. And then we do have a v that's being multiplied in there as well. So that just stays right there with that term as v. And that's it for that term. And now we're going to multiply 2u times this last term. So there's no coefficient in front of b squared, so it's an understood 1b squared. So 2 times 1 is just 2, positive 2. And then we don't have, like, variables, so just like in the last problem, we're just going to put them together like this, u b squared. Typically speaking, we do want to keep the letters in alphabetical order. So even though b has a higher exponent than u in this last term, u comes before b in the alphabet, so we keep it in that order. And that's it. That is how we multiply monomials times polynomials. So now on this next page, we're going to reverse that. We're going to go backwards. So we've got some problems here that are already combined, and we're being asked to factor the polynomials. So we are going to be finding the greatest common factor, the GCF, in each of these terms, and basically reversing what we just learned how to do by multiplying them together. So what we need to do in this first problem, again, I have sort of an easy, medium, and hard problem on this page, so we can kind of work through those. What we need to do in this first problem is figure out what is the common factor, the greatest common factor, for both of these terms. What can we divide out of both of these terms evenly? So for 8, we don't have any variables there, so we're just going to worry about just the coefficient or the constant, the number part of it here. So with 8 and 6, the biggest common factor that we have is going to be 2, right? 4 also goes into 8, but it doesn't go into 6. So we can think about it like this. I write it like this a lot when I'm working with students and teaching them this skill. I write it like this. I'm going to divide this by 2, and I'm going to divide this term by 2. And here's how we rewrite that. We're going to pull that 2 out, and whatever is left after we divide by that 2, then that's what's going to be left over and go in this set of parentheses here. Again, remember that we're kind of working backwards from what we just learned on this page. In this page, we were taking whatever was outside of the parentheses and putting it in and multiplying it in. Now we're taking whatever can be divided out and pulling it out of the parentheses. So 8 divided by 2 gives us 4, and then plus 6 divided by 2 gives us 3, and then that x to the 4th is just going to stay with that 3, because we can't divide any number of x's out of this because the 8 didn't have any x's. So it has to whatever we pull out of the parenthesis, it has to match for both terms. So that's it. That is factored as much as possible. All right, let's take a look at this next problem. Take a look at this next problem. See if you can look at just the coefficients. Just worry about the coefficients for now, and then we'll get into the variables. What can we pull out of each of these 3 numbers? So it looks like to me 7 is going to be the greatest common factor for each of these. Each of these numbers are divisible by 7. And if you're working on this and you just can't figure out what a certain number is, that whatever your greatest common factor is, if you can at least start with any factor, even if it's smaller than the greatest common factor, you can at least start there and then make your numbers a little bit smaller. That might help you. We'll get into that, like that sort of method in the next problem, because I think 7 is really the only number, the smallest and the greatest number that can be factored out of here, except for 1, of course. All right, so we're going to divide each of these by 7 for sure. Now let's take a look at the variables. So each of these has at least one m that's being multiplied times it. So the rule is for the variables, you can only take out the smallest exponent of the variables, meaning that this m right here is really m to the 1 power. So that's the most that we can take out of here, because if we were to divide by anything greater like m3 or m4 or m5, whatever, we can divide that out of these 2. but we can't divide it out of this one. So it has to be the same for all 3 of these terms. So m is the most that we can take out of each of these terms for the variable. So let's write that outside of the parenthesis and then see what's left over. So 63 divided by 7 is 9. M to the 6th power divided by m is going to give us m to the 5th power. So that's 9 m to the 5th. Minus 49 divided by 7 is 7. M to the 5th power divided by m, that's going to cancel out one of those m's, leaving us with 4 m's that are being multiplied together. So that's m to the 4th. And then minus 21 divided by 7 is 3. And both of these m's cancel out, so we don't have any other variable with this last term. So that's it. That's as far as we can go with that one. All right, our last problem, our most challenging problem, is take a look at this again, see if you can figure out what our greatest factor is. All of these numbers, all of these coefficients, the 24, the 36, the 60, they all have a lot of factors. So kind of what I was saying before, if you're not sure what the greatest common factor is, just pick a factor that can go into these numbers. And then you'll at least reduce these numbers down a little bit smaller, and then hopefully be able to see other numbers that you can factor out. So I think that 12 is the greatest common factor for this one, but I'm gonna show you what it looks like if, let's say, we just factored out 6. Like, let's say we recognize, oh, 6 can go into all of these numbers. Let's factor out 6 and see what happens. So just focusing on the coefficient part, on the number part, and then we're going to do variables separately. So now let's take a look at our variables. We've got a squared, we've got a b squared, we've got a single a, we've got a single b, and we've got a single a, no b in this term. So that tells us that the most we can factor out as far as our variables are concerned is 1a, one simple a. All right, so let's see what we get. So we've got 6a on the outside. Negative 24 divided by 6 is going to give us negative 4. And then a squared divided by a, that's going to get rid of one of those a's. B squared just stays with that. Plus 36 divided by 6 is 6. And those a's are going to cancel out, leaving us with just b. And then 60 divided by 6 is 10. And those a's cancel out, leaving us with just 10. Now, we have factored this, but we haven't fully factored this. We can see now that we've got 4, 6, and 10. So that means because they're all even numbers, we can factor out more. So this is kind of what I was saying is like sort of like when you're simplifying fractions. Sometimes it's hard to see what we can simplify by, like that greatest common factor that we can simplify by. So you just start with what you know, and then your numbers get smaller. They're a little bit easier to handle. So with all of these, I can factor out an additional 2. So 2 is going to come out of these numbers. Now, when I rewrite this, 2 is going to be multiplied times that 6a that's already outside of the parentheses. So negative 4 divided by 2 is negative 2. We haven't factored out any other additional variables. So the variable part is just going to stay the same. And 6 divided by 2 is 3b. And then 10 divided by 2 is 5. So we've got that. And so now we can see, well, 2 and 3 and 5, greatest common factor for those is 1. So that's as far as we can go. We do want to simplify this part a little bit more and just multiply that together. So 2 times 6a is 12a. And I'm just going to rewrite all of this inside the set of parentheses. And that is a factored expression. I think, yeah, okay. I don't have anything else for us for tonight. Thanks so much for joining me. I really do appreciate it. Let me know what you thought in the comments. If you're watching this on replay later on, let me know what you think in the comments. Don't forget to like and subscribe. That does really help me. And if you find that you're needing more support with math, then feel free to reach out. I'd love to see if I can help. Until next time, I'll see you next week. Bye.